25 May 2023. The Fourier analysis. So reading about the Fourier analysis has basically been the idea that what goes into the development of, first of all, even the development of the integral calculus, and the differential after a model of numbers and relations or function. Mixed for that, there's then only so many kind of fundamental theorems about what the development for a series, their existence and their equivalence and equality to a value of another function in terms of its integrals and derivatives, an infinite sum of those, and it means to compute the coefficients of this series in its terms, and these multipliers inside or factors in the terms for these orthogonal functions and their weights, and the orthogonality that their product as about two spaces is 0, and then normalization that by the integral of 1 by its weight is 1, then make for it's able to implement that as a sort of window, and as was seen in this development of the Fourier analysis, so that what results is not so many theorems necessary and not so many properties that are particularly unique to Fouriers and Euler's and Gauss's and Dirichlets and Riemann's and Lebesque's theorems, as about the definitions of the integral and the definitions of convergence and the definitions of the convergence of the series, the definitions of the convergence of the values is about that it's the envelope makes like so, and it's in delta epsilonics usually framed, which is available, or that otherwise means via convergence are available. That the idea is to figure out how that works out, that the Fourier analysis then also becomes kind of the Fourier second analysis. How to establish for other systems of theorems and equations or result a similar analysis, but in particular terms that might be more convenient or relevant to other systems, and when, for example, then those are closed or finite, making for closed forms, which is a lot of the goal of differential geometry, and its submersions and immersions, and the way that it kind of curtails some aspects of features of functions. Here, as was talked about, the piecewise, for example, that is sort of limited at about 0 and infinity, the derivatives. That makes for closed forms, and it makes for a bunch of different ways to make things easier, and in a systematic manner. That the template of the derivations becomes a placeholder for other equivalent models of objects that have the same connotations, implications of the derivations, leading to results proved having the same properties, and thus in a sense interchangeable about these things. This is in the notion of like the hyperbola hat series, the non-standard, where there are, of course, already a bunch of different families of orthogonal functions, implement any of all sorts of transforms, and such. So we got up to this question about let's see, example 2.10 about the periodic extension of the function defined by fx equals e to the x satisfies the conditions of theorem 2.2 as we'd already kind of got up above about employment of the small angle approximation, that as theta goes to 0, that theta over sine theta goes to 1. In a very small region there, so it's only kind of used in the middle of things, as it were. About the Dirichlet kernel. And about the Dirichlet kernels, basically that's where the wide window is that results that for the very wide window compared to the region of analysis or the bounds, that what so is holds. That because both reading on because both the e to the x and the negative x are differentiable everywhere, and then e to the absolute value of x has a right-hand derivative at negative pi and a left-hand derivative at pi. Moreover, f is continuous on R, since f negative pi from the right and f of pi from the left equals e to the pi. Hence, the Fourier series found converges for any x in R, and we have e to the absolute value of x equals 1 over pi, e times e to the pi minus 1. Now I'll be curious for this because I've been looking for things relating to x times ln x quantity minus 1. X times the quantity ln x minus 1, because it's the integral of ln x, which is the integral of 1 over x. Vis-a-vis that the notions of the integrals and antiderivatives of the powers in terms like square and cube and so on about acceleration in terms, and the inverses of that in terms of what those would add up to and what happens when they each kind of cross a line over to each other, and how that would add up to those, about the inverses of things come together in terms of differentiation and integration and the impulse. So e to the absolute value of x equals 1 over pi, e times the quantity e pi minus 1, plus 2 over pi, beginning the Fourier series, sum from 1 to infinity, negative 1 to the n, e to the pi minus 1. I wonder, and don't, that this quantity over 1 plus n squared times cosine nx. Of course, if f is piecewise continuous on negative pi pi, it is integrable there, and we can state a simpler looking version of theorem 2.2, one that does not highlight the local aspect of convergence, but is quite sufficient in most applications as follows. Let f from R to R be a periodic function of period 2 pi that is piecewise continuous on negative pi pi, then its Fourier series on negative pi pi converges to the value 1/2 of f x from the right plus f of x from the left at every point x and R, which f has right-hand and left-hand derivatives, da da da. Now this is similar to the definition of the right-hand and left side from Formula 9 here, about that in the piecewise they're not asymptotes, but you kind of assume there are, and so functions still continuous in a sense. Piecewise functions being continuous at the places where they have these removable discontinuities, the piecewise continuous in the Riemann integration or the vertical lines. And no places that there aren't any holes in the surfaces. That said, it's not possible for a Riemann integral in this manner to have a removable region within, otherwise its integrable region. It would have to be kind of transformed out, or otherwise transformed into a manner such that it was still Riemann integrable. The author continues, there are several other theorems giving sufficient conditions for the convergence of a Fourier series at a point. Some are applicable when others fail. Most of them are beyond the scope of this book and will not be presented here. See, for instance, a Zygmund trigonometric series. Second edition, volumes 1 and 2. CUP, Cambridge, Mass., 1988. Most of them are beyond the scope. We shall prove only one such theorem, discovered in 1867 by Rudolf Sigismund Lipschitz of Bonn. It is actually a particular case of a result obtained in 1880 by Ulisse Dini of Pisa. Theorem 2.4, the Lipschitz test. Let f from r to r be a periodic function of period of 2 pi that is integrable on negative pi pi. Then its Fourier series on negative pi pi converges to f of x at a given point x in r if f is continuous on an arbitrarily small interval centered at x, and if there are positive members big M and delta such that the absolute value of this quantity fx plus t minus fx is less than or equal to absolute value of mt for t and delta, negative delta delta. So this would be similar if not only in the variables named, the previous derivation is after the Dirichlet, the Riemann. This looks like one of Riemann's approaches. So then I would gather that he would have it from here first. That sometimes when you find these proofs, it's like, well, it would kind of have been better that this proof was shown first because it kind of uses the elementary approaches. This series minus fx equals 1 over 2 pi, and the integral from 0 to pi of this bracketed quantity minus 2fx of the Dirichlet kernel t dt. If m and delta are as above, and in addition delta is so small that f is continuous on x minus delta x plus delta, then the function on t is defined by f of x plus t plus f of x minus t minus 2fx over that all t is integrable on 0 delta because it's continuous there and bounded by plus minus 2m. Indeed, fx plus t plus fx minus t minus 2fx is less than or equal, that's absolute value of it, less than or equal to f of x plus t minus fx plus f of x minus t minus fx. And all that's less than or equal to 2m, absolute value t. The quotient above, this fx plus t f plus fx minus t minus 2fx, is also integrable on delta pi because f is integrable and delta is between t and 0 on this interval. Therefore, it is integrable on 0 pi. Since t over sine half t is also bounded and continuous on 0 pi, the Riemann-Lebesgue theorem gives limit from n goes to infinity of 0 to pi f of x plus t plus fx minus t minus 2fx over t, that quantity, times the quantity t over sine 1 half t times sine of the big N plus 1 half t dt equals 0. He has an example as about when f of x is x sine x, x sine 1 over x when x is not equal to 0, and 0 when x equals 0. It's bounded continuous on negative pi pi, but does not have one-sided derivatives at the origin, since h sine 1 over h quantity over h equals sine 1 over h has no limit as h goes to 0, either for h greater than 0 or for h less than 0. Though if you treated it like 1 over h sine 1 over h, and if that was small, if h is small, it would kind of have that, the small angle approximation. And then the why not is so for large kind of helps explain why it's kind of funny that the window balloons and is used for the Riemann-Lebesgue convergence, but in a similar case when sine being arbitrarily large is or sine rather of an arbitrarily large value is still between -1 and 1. Why it can't just be contrived that it's an arbitrary number of even, if it's some even thing that's precise enough, far enough out. You could say that it's so, and if this was in integer terms or it multiples of 2 pi, it would be the same. And then there's a notion of otherwise it would just be the same as h, and its limit would be 0. There's the complementary sine function, it's sine x over x. So sine x over x as x goes to 0 is like infinity, you know. But as it goes to 2 pi, say, it's 1 over 2 pi. With the idea of that every 2 pi radians, sine is 1. Or rather, the sine of theta equals over theta equals 1 over theta. Again, speaking to that, then, well, what if theta is very large? Won't that again be 0? Gets into an idea about how to have a non-standard extension of the small angle approximation for the large angle approximation being the same, or actually that it's 0, because it would be 1 over theta for large theta. And about the same as the complementary sine function, or sine c, it would be the same. Anyways, carrying on. Has no limit as h goes to 0, either for h greater than 0 or for h less than 0. Thus, theorem 2.2 is not applicable in this case at x equals 0, but f satisfies the inequality in theorem 2.4 at the origin with m equals 1, because f is 0 plus t minus f0, that absolute value equals this quantity, absolute value t sine 1 over t. It's all less than equal to absolute value t. Hence, the Fourier series of f on negative pi pi converges to f0 equals 0 at x equals 0. Thus, it is still 0. Where the idea is that as 1 over h goes to 0, that it would be a very large angle. And that 1 over h would be very large. So it seems to be here there's variation. So that's, and this is outside the usual context, to be sure. And although any mistakes are my own, it's still so that it's there are two sides of it outside. Hence the Fourier series converges. We conclude this section by outlining some of the most relevant results on the pointwise convergence of Fourier series since the time of Dirichlet and Riemann. Even in the absence of proof, it was thought for some time that the continuity of f was a sufficient condition for the convergence of its Fourier series at all points. This conjecture was disproved in 1873 when Paul du Bois-Reymond gave an example of a function bounded and continuous on negative pi pi, but whose Fourier series diverges at the origin. Then, 3 years later, he exhibited another continuous function such that in any neighborhood of an arbitrary point of its domain, there's at least one point where its Fourier series diverges. Well, that's interesting. Paul du Bois-Reymond is well known for his infinitar calcul and his approach to an attack on the non-standard and trying to get to it and understand it. He's got the long line where the space of all real functions by their variables are basically put in a trichotomous order as if they were on the real line. But because the space of the functions from real numbers to real numbers is greater than the space of the real numbers, it's cardinal. The cardinal is greater, but it's still that they all cross the line. It causes some consternation to people because Paul du Bois-Reymond's long line on the reals is bigger than the reals. Yeah, it's the same. But anyways, but here I'm happy to see that he's also been involved in this showing counterexamples or exceptions to otherwise what are these developments, because those make for mathematics and the singular points, and where it's necessary to know sufficiently the reasons why the derivations hold or don't hold, so that the rogue wave or the exception makes its own rule. For a long time, it was not known whether or not the Fourier series of a continuous function must converge even at a single point. This question was settled by Lennart Carlsson in 1966 when he showed that if f squared is integrable on negative pi pi, even in the wider sense of Lebesgue to be explained in 2.9, this Fourier series converges except possibly on a set of measure 0. Of course, a bounded continuous function is square integrable, and Carlsson's theorem applies in this sense. Well, I would say that was already kind of shown up about this convergence of the series and the existence of the convergence of the series. Even at a single point. I suppose that's what's about point-wise. Of course, a bounded continuous function is square integrable, and Carlsson's function applies in this case. However, Carlsson's result is the best possible for continuous functions in the sense that given a subset S of negative pi pi measures 0, there is a function continuous on negative pi pi, and whose Fourier series on negative pi pi diverges at every point of S. This was shown by Jean-Pierre Kahane and Yitzhak Katznelson in 1966. Outside of the class of square integrable functions, the worst can happen, to wit, in 1926, Andrei Kolmogorov, when a young man of 23, gave an example of a function integrable in the sense of Lebesgue and whose Fourier series diverges at every point. So it's always nice when the author lays out a development that says, oh, by the way, there are arbitrarily contrived functions that are either pathological or exceptions, and if you're able to develop for some of these sorts of functions why they have their own sorts analytical bases and can break out and relate to, back to the Fourier series, then it's possible to kind of either put them back together or show that they're distinct and unique, and you need both of them to prove a wider class of problems solved. That's as much a starting point for further development as much as a sign that says the world ends here. It's not so. It's just that you will fall off. You have to bring your own bridge. This is only a bridge. That's how it goes. Up to this point, we have considered a function defined on negative pi pi and its periodic extension to period 2 pi. Generally, you must consider a function defined on an arbitrary interval, f from alpha minus a, alpha plus a, goes to r, a greater than 0, and its periodic extension to period 2a. If we introduce a new variable, y equals pi over a times the quantity x minus alpha, to find a new function h by hy equals fx, then h is defined on negative pi pi. If f is periodic of period 2a, then h is periodic of period 2 pi. Also, h has one-sided derivatives at y if f has one-sided derivatives at x, and is piecewise continuous on a small interval centered at y if y is piecewise continuous on a small interval centered at x. If y is such a point, theorem 2.2 gives the coefficients for the Fourier series and the formula for the estimation or averaging of it from the left and right, and the sum of from the left and from the right, and the same as the Fourier coefficients. Undoing the change of variable, these become then it's 1/2, f x from the left, x from the right, equals 1/2 a naught plus sum from n equals 1 to infinity of this bracketed term, a sub n cosine n pi over a times x minus alpha plus bn sine n pi over a times x minus alpha, where the a sub n is equals 1 over a, integral from alpha minus a to alpha plus a of x cosine n pi over a, quantity x minus alpha dx, and bn equals 1 over a, integral from a minus alpha minus a to alpha plus a of fx sine n pi over a, x minus alpha dx. Now, what I'm curious and interested about the periodic functions is this kind of thing. Earlier there was a discussion about this trigonometric and the sine and the sinusoidal, and about how that's drawn out as about like Pythagoras' theorem about what is the hypotenuse being the length of the circle, and thus the various arms that represent their on the course of the circle, solving by the equation of the circle, getting back to what would be the value of sine or cosine, trigonometric functions. Then the idea was this, that if you take instead an equilateral triangle and start as if it's set in a line, and then you unhinge it on the left and start unrolling it to the right as above the line, and then when that reaches reaches that you trace that, then when that reaches back to the line, and then if you flip that over, kind of in a sense, starting the same way as you would just for a line segment, just flipping it over and tracing at the end, flipping over the tracing the end, this kind of thing, that it draws for this equilateral triangle, the same thing as all these right triangles do about the circle, when it traces out the value of the length of the hypotenuse, or rather the length of the ordinate, or the abscissa, if you'll excuse me, thinking onto it, for sine and cosine respectively, not the hypotenuse. But the idea is that this function can also be written out this way. So it's a parametric term that is essentially is based off the period first. And so if you start with just a line segment and trace that about, it would draw a half circle over the line, and then you flip that under, and then you trace that under, and then you flip that over, and then you trace that over, and then you flip that under. And it really reminds of those little it's kind of like one of these toys, and it's taped together, and the way that it's taped together makes that each of these links in the chain, that if you flip it over, then it will, using the same piece of tape, it will flip back and forth, flipping under and over from the left to right of this thing as gravity pulls it down, and then its collision with the next one knocks that out, and then it flips over and back and forth. Now I'll need to research and find out what the name of this type of paper tape link chain is, because it's a similar type of notion to this alternative method of drawing a wider family of curves that include the sinusoidal curves sine and cosine by their shape. And that when we look to, in terms of defining things by their period and amplitude, and with regards to 2 pi being about the period of revolution about a circle. But what we're interested in is these half periods of whether a half turn is defined as the turn, or whether it's a turn is defined as 90 degrees or 180 degrees or 360 degrees. I can't really imagine somebody define a turn as 270 degrees, because it's not really around in a sense, or away. It is, because it's the same. It's orthogonal and perpendicular as 90 degrees. This is we're familiar with, or pi halves radians. The angle, the dimensionless angle. Here the idea is to figure out that, and this is irrelevant in a regular enough sense, because where I'm going with this is that then what I want to figure out is that starting with just a segment, or the n-gonometry, is just this line segment, and it draws a semicircle above the line, it flips over, it reconnects, it draws a semicircle beneath the line, it flips over, reconnects, ... So if there was a triangle that was unfolded and had the same length as this as twice that line segment, then it would draw this sine function above the line and then under it, but it would also be as under this circle. And so it would kind of be within that, because it's kind of like the sinusoidal hump inside, otherwise the ballooned out semicircle. So the idea is to compute that as a parameter in a function. What's the difference between the sine and the circle in that sense? To make it possible to make it so that when there is something that you really have like just a semicircular curve for whatever reason, it's like a snake, it's like an inchworm, it's wiggling or what, and that's how it goes. It's oscillating and recitative, you know, vis-a-vis that it's traced out by this sinusoidal, or it's like the motion of a pendulum traced over time, left to right, dot dot dot. You know, for all the usual fundamental equations of wave motion, and all the usual way that their basis of restitution and oscillation is sine. That there's also a way to build it up as about this 3-gonometry or trilateralometry, or this trirograph, I suppose it were, like the spirograph, but a trirograph here. Trilateralometry, and I call it n-gonometry, for the applicability then of it to quadrilaterals and pentagons and hexagons and heptagons and dot dot dot. Any regular polygon is figured to, it follows this algorithm of unfolding it, tracing out what that does when each of the angles is evolved at the same rate, flipping that over, unfolding it back under, that it draws a symmetrical or not function that way. I haven't really tried it yet. I imagine it can be done kind of with toothpicks or something like that, or very simple programs should be able to carry it out quite directly in terms of drawing the thing. This is about when, otherwise, as we've been talking about making derivation of a Fourier analysis, this is like a Fourier analysis specialized to a world where there's only these particular periodic functions available, and so anything that has to do with that in terms of this entire development would have to otherwise be implemented in this way instead. So it's possible, and it's an exercise, and it wouldn't necessarily be, you know, the first thing that comes to mind, especially when, you know, all the accumulated wisdom and proof and the relayed wisdom in the curriculum is dedicated to this existing way, which it is. It's still, when trying to figure out then adding something to mathematics, that it makes for a way. And because it's in quite simple and general terms, then it doesn't have to bend too much without breaking, as it were, to apply to all these other kinds of different derivations and act as a model for the object, otherwise in these derivations, about like to so, making it like so. And then that they can be parameterized, because the trigonometric functions as parameters are basically like, it says of tracing about a circle, that according to this angle, that the angle is the result of these ratios of the sides, which are defined by Pythagoras and the Pythagorean theorem as about the circle combined, which is great. The idea is to figure that out, and then also what happens when these other variables change, and besides that, to show why and what is the scale of things with regards to an equilateral triangle of unit side lengths and a right triangle of, say, that its isosceles sides are a unit side length, or that its hypotenuse is a unit side length, or that its perimeter is 3. These kinds of things. So y equals pi over a times the quantity x minus alpha. This substitution in terms changes the period of this evaluations from 0 to 2 pi, or as about from negative pi to pi, from negative a to a. and that its period is 2a. And that ends up being a lot simpler later because then you can use it for usual things when they're just the terms are modular or periodic in integers instead. The constants a sub n and b sub n defined above are called the Fourier coefficients of f on alpha minus a alpha plus a, and the right hand side of 10 is called the Fourier series of f on alpha minus a alpha plus a. It's also just so that above the constants a sub n and a sub b sub n are reused, and they're called the Fourier coefficients here on alpha minus a alpha plus a vis-a-vis negative pi to pi, and so on. Similarly, when the Dirac delta function, which is understood here as a spike at the origin with area 1, that's an infinite spike at the origin with area 1, that it accepts the second parameter, it's offset left to right. So this is basically, after having built a window about the origin, moving the origin left to right by changing the coordinates. So it's really moving the origin, the analytical basis and the origin, and where the kernel lives. Anything that was built about the origin in arbitrarily small numbers, this is moving it. But with those concerns or concepts left out, then it's just translating it with a substitution of variables. There is a wider context. Let theorem 2.5, let f from R to R be a periodic function of period 2a, a greater than 0, that is integrable on alpha minus a, alpha plus a. Then its Fourier series on alpha minus a, alpha plus a converges to the value 1/2 fx plus 1 plus fx minus. So this is kind of just restating the same results so far we got, that Fourier series converges. It exists, it's the value in this interval it converges, and from the left and right it converges. In a similar manner, we can prove the analog of the Lipschitz convergence criterion, Lipschitz test, for f from R to R be a periodic function, is integrable in its Fourier series on alpha minus a, alpha plus a converges to fx at a given point x and r if f is continuous on an arbitrarily small interval centered to x. There are positive numbers m and delta such that fx plus t minus fx is less than or equal to mt for t and negative delta. This is basically just when you have a function that's of arbitrarily high difference, but as long as it's still continuous, and it can have an arbitrarily high derivative, which would otherwise kind of break it out the window. It's kind of just stacking it way up above here, so it's putting Lebesgue and Riemann together in a sense for Lebesgue and Riemann integrability, and taking that when it was hold so and fixed here this way, that then it's not going to squeeze or stretch it out of what it was its window. Though one could argue that those two results would have to be built together, and with regards to the previous talk's comments about the arbitrarily larger and the arbitrarily larger, and having to redo the definition of some other thing changed, here this would kind of have to be added into it. In such the case otherwise, like when I was saying that Emile Dubois-Riemann showed that there's something that kind of breaks the window and breaks the box. It's like so. So it's in the window, it's in the box. Small intervals centered at x if there are positive numbers, m and delta, and it's about the same, except just translated about the coordinates and multiplying out for a as the previous notion. Find the Fourier series of the functions fx equals 1 between 4 and 5 and 2 and 5 and 6. And so at 5, it will be the average of from the left and from the right. And in terms of the Fourier series and the coefficients, and it just takes the integral of f of x as piecewise, and then it just adds up the a sub n's and the b sub n's, and gives the averaging term, and then at x equals 5, the sum of the series is 1.5. And so that the sum of the series is 1.5 is like, besides saying here's the Fourier series, it's an infinite series in sum. Also, it's 1.5 at this particular point, so you can kind of say that this infinite series now adds up to this, which is kind of nice. For defining functions that have Fourier series of particular contrived forms and saying, oh, now this is an infinite series for it, whether that's useful, Consider next a function f defined on an interval 0a. It can be extended to the interval negative a as an even function, or as an odd function, or in any other way, and that each of these can be extended to the whole of R as a periodic function. Of course, the function must be defined to have the value 1/2 of this quantity f of x from the left, x plus f of x from the right, at any point x of this continuity that may be created in this extension process. So the function is defined kind of like Heaviside step. Goes from 0, it's 0 on the left of the y-axis, and it's 1 to the right, and it has a step of height 1 at 0 on in x, upward in the y dimension. This makes the opinion that f of 0 equals 1/2. Not that f of 0 is the range from 0 to 1. Because there isn't really a usual and continuous notion that says, you can't really write an asymptote or a vertical line in this way, so just make it a range. But here it's like for this Fourier period that he's defined as so. These functions are piecewise, and so he just says that he has it like so, and then the Fourier terms will add up to it and be like so. And then he has kind of like one of these triangle sawtooth waves. Whereas if you turned it over, it would kind of look like the orthogonal 90-degree bend of an orthogonal basis. And then if you just kind of relax that into where the at 1,1 was kind of the center there, if it just kind of became a hyperbola or looked like 1 over x like that, this is kind of like these triangular waves or sawtooth waves, triangular waves. And the other one is a ramp. It's just a repeating ramp from -1 to 1. It goes from -1 to 1, and then it drops back down to -1 and repeats every 2a. Another one is sort of this, it's an upward ramp for 1 and above the axis, and then there's a lower ramp for 1 below the axis, so it's sort of odd. And then it just has like this teeth above and below. And then the last one is kind of it looks like a sinusoidal wave. It's just a triangular wave below, and then a triangular half wave above. So, and as to whether the period when the function is even and it stays above, then whether that really has it has a period of revolution a. Then as to whether if you were to treat it as odd, that it would have to have 2a. This is the kind of thing that would make it for being able to treat any of these kinds of different simple waveforms more generally. But that otherwise the ones that are repeating even every half interval, and you can imagine a periodic function that has a period 2a, but if it's something like sine billion pi, it also or excuse me, sine billion x, then it also has a billion revolutions in that same period. So you could break that up and treat it kind of arbitrarily, those being arbitrarily small. You might have to redo some of the derivations otherwise for an analytical basis than Dirichlet kernel, but modularity is a regular and self-similar property, like multiples of 10 and powers of 10, and multiples of powers of 10, and powers of 10. It's modular and self-similar. And it's very, very much so. It's about the field and the fractions and their fractions. So ongoing, he presents some examples. Rodriguez, Gonzalez-Velasco. Gonzalez-Velasco continues to present these examples. And I'm enjoying this so far, and I'm curious to get up to some of the more historical bits. In connection with the odd and even extensions mentioned above, the following terminology is sometimes useful. If a greater than 0, let f0a r be an integrable function, then 1, the Fourier sine series of f on 0 at a is the Fourier series on negative a of its odd extension, negative aa. That is, you only need the one or the other, the sine or the cosines, for these even or odd functions. So I may have heard that before. It's not an unusual thing, and it ends up making it possible. You don't have to deal with this or those or the others. So the Fourier series is the sum of the Fourier sine series and the Fourier cosine series, which are the same shape, only offset by pi halves phase, or negative pi halves, I forget. Maybe that's where the 270 comes in for a term. So, section 2.6 is the Gibbs phenomenon. So, when I think of Gibbs, it reminds me of like Gibbs ringing or hysteresis. In a practical situation, a Fourier series cannot be used in its entirety to approximate a given function, since one must necessarily take only a finite number of terms. This raises the question of how well a partial sum of a Fourier series approximates the function to which it converges. So this is part of the theory of asymptotics and approximation theory in computing the bounds of the error term. Whatever's left after computing the first so many terms that in their infinite series goes to this value, it converges to this value, is left over is the error term. Contributions that were not included but have analytical character. In 1898, Albert A. Michaelson and S.W. Stratton of the University of Chicago expressed their dissatisfaction in a letter to Nature by pointing out that the approximation is not good enough near a jump discontinuity. Experiments with their harmonic analyzer show this to be case for the function of example 1.6, even after taking 160 terms of its Fourier series. An explanation by the Yale professor Josiah Willard Gibbs appeared in the same magazine the following year. Gibbs considered the periodic extension of the function defined by fx equals x on the interval negative pi pi, which satisfied the conditions of theorem 2.2, and pointed out that in the neighborhood of any point of discontinuity at x naught equals 2k plus 1 times pi, where k is an integer, and for n large enough, there are points x1 less than x0 and x2 greater than x0, such that the series for x sub 1 is approximately equal to 1.18 pi, and the series for x2 is approximately equal to negative 1.18 pi. That is close to x naught, and on its left side, the value of the series exceeds that of f of x from the left by about 9% of the value 2 pi of the total jump at x naught. Similarly close to x naught, and on its right, the value of the series overswings the value of f of x from the right by about 9% of the total fall at x naught. This situation is illustrated. And so the illustration of the diagram shows a ramp, and then the function at the piecewise discontinuity is the start of the ramp back up. So it's kind of like the ramp function from negative 1 to negative 1 to 1, 1, and then at its discontinuity, it drops down 2, and then again, a copy of the same waveform occurs. And so the drawing out the Fourier series over it for these terms, the initial terms, shows that it's kind of wavy or snaky or coily about the this ramp function, and then at the very end, before it falls down, it's above it. This is called overshoot or ringing, and hysteresis. And as the author calls it, overswings, but it's called ringing or overshoot or hysteresis. And hysteresis is also a more of a general term, kind of like ergodicity is a general term, entropy is a general term, but overshoot and ringing is usually associated with the Gibbs phenomenon. And anyway, that in the middle, as it falls, it also happens to cross right through in the middle, that spot at the origin where the average of otherwise the terms is. So as it goes through, it's still good in the middle of nowhere. It's just overshoots to fall back inside. The remarkable thing is that, as we shall presently see, this overswing remains constant at about 9% independently of n, although the points x1 and x2 at which it occurs become closer to x0 as n increases. So that's interesting. The remarkable thing is that this discrepancy between 1 pi and 1.18 pi is that the less terms that are computed, the farther away it is. It jumps earlier for it to hump over the edge, as it were, and to drop back and make its way back down. So anyways, why is that the value instead of a constant value? I don't know. I'd be curious, because really all I want is an analytical form for explaining what that value is and why it is. Had Michaelson and Stratton added many more terms to their partial sum, they would have been equally dissatisfied. This is an inherent imperfection of Fourier series and not just a matter of how many terms the approximating partial sum contains. The presence of this overswing is usually known as the Gibbs phenomenon. And again, this is only present when these waveforms are like discontinuous and piecewise in this sense. It's smoother about the smooth bits. Approximating partial sum contains. The presence of this overswing is usually known as the Gibbs phenomenon, although it had been discovered early in 1848 by the English mathematician Henry Wilbraham. Wilbraham's work remained largely unnoticed, and Gibbs was unaware of it. To demonstrate the appearance of the Gibbs phenomenon, we shall find it convenient to consider the function defined by f of x equals 0 from negative x to 0 and 2 pi from 0 to pi, rather than Gibbs' original example. By the theorem, its Fourier series converges to pi at the origin and to f of x at any other x in negative pi. So he's basically translated the whole thing up one. To study the behavior of this near the discontinuity of the origin, we use limit 2, we obtain, this is where he's replaced by x by t minus x, and later he's going to replace it by t because he's kind of making a box for it, and then it's going to kind of fit in the box square. Series equals 1 over 2 pi integral from negative pi to pi of ft Dirichlet kernel t minus x dt equals integral from 0 to pi Dirichlet t minus x dt equals integral from negative x to pi minus x of Dirichlet u du equals integral from negative x to 0 of Dirichlet n plus integral 0 to pi of Dirichlet n plus integral of pi to pi minus x of Dirichlet n equals 0 integral from 0 to x of Dirichlet n plus pi minus integral from pi minus x to pi Dirichlet n, where the value pi for the second integral has been obtained from equation 7 on page 38, this average function, and a reversal of the limits of integration in the first possible because dn is an even function. So it's making use of symmetries about the even and odd, and thus the ability to kind of cancel it back out and make a pair product and double it. Since we are interested in values of x near 0, the interval between pi minus x and pi does not contain the origin, and d sub n is the product of cosecant and inverse cosine, inverse sine, 1/2 t, which is integrable over this interval by sine of the large number, infinity plus 1/2 t. Thus the third integral tends to 0 as n goes to infinity by the Riemann-Lebesgue theorem, and the series approximately equal to 0 to x of Dirichlet n plus pi for x small and n large. Phenomenon is already apparent from this approximation, the geometric approximation when x greater than 0, the area under the graph of Dirichlet kernel from 0 to x increases with x until x equals 2 pi over 2 infinity plus 1, where it reaches a maximum. Then it decreases as the area between the x-axis and the first ripple of dn is incorporated in an integral with a negative sign. In this manner, the presence of the ripples of the Dirichlet kernel, alternatively negative and positive, is translated in the maxima and minima of the integral from 0 to x of dn. The portion of the graph for x less than 0 is obtained from the fact that dn is an even function. In order to estimate the value of the first maximum, which is clearly the largest, we must find the approximate value of the integral from 0 to x of dn for x greater than 0 by analytical means. We have this integral of Dirichlet kernel dt plus 2 integral of Dirichlet kernel, or excuse me, integral of sine n plus 1/2 or t over t dt, not the Dirichlet kernel, plus the integral of t minus 2 sine half t over t sine half t, times sine n plus 1/2 t dt. Now, if x is small enough, the factor t minus 2 sine 1/2 t over the quantity t sine half t is continuous on 0x, and by L'Hopital's rule, approaches 0 as t goes to 0. Now, just like Rolle's theorem, I need to understand L'Hopital's rule a little bit better because it's very widely applied. And with that, the sandwich theorem, L'Hopital's rule, Rolle's theorem, these are the kinds of things that I want to have very much facility with, and to understand their limitations particularly. Because in this course of the understanding of the Fourier development, it's starting to become clear some of the issues that come on in the boxing and the windowing and the hysteresis, or ringing and overshoot, and what it means about even and odd functions, and then what it would mean about transformation of coordinates, and here transformation of coordinates about the even and odd, but also rotations and these kinds of things. About the Dirichlet kernel particularly. That, as he goes on to say, and the second integral on the right-hand side above approaches 0 by the Riemann-Lebesgue theorem. We conclude that for x small and n large, that the series for x is approximately 2 integral from 0 to x sine, or Dirichlet kernel dt plus pi equals 2 integral 0 to infinity plus half times x, or a large number, the window, sine u over u du plus pi. If we denote the right-hand side by psi x, we can construct its graph as follows. Clearly psi 0 equals pi, then we can compute psi t of x, or excuse me, psi prime of x equals 2 sine of this quantity. He just kind of takes the derivative off out of it. Oh, after as an integral, he computes his derivative by taking it out from the definite integral and making it like so. And this is about the differintegral systems, or integral equations for differintegrals of the pre-derivative vis-a-vis taking the derivative and taking the integral, and when a value has thing. But it seems fair, right? And so psi prime x for x not equal to 0, and psi prime 0 equals infinity, 2 infinity plus 1, or 2n plus 1. It's large. The last value is the slope of psi at the origin. Its relative maxima and minima occur where psi prime x equals 0, that is x equals k pi over this quantity n plus 1/2 for every non-zero integer k. Examine the second derivative shows that psi has a relative maximum for da 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 and a relative minimum for k. Examination of the second derivative shows that psi has a relative maximum for k equals -6, -4, -2, 1, 3, 5, and a relative minimum for -3, -1, 2, 4, or seemingly maxima for even odd numbers and or even negative numbers and positive odd numbers, and minima for negative odd numbers and positive even numbers. From the fact that according to theorem 2.2, the Fourier series is close to 0 for x less than 0 and closer to pi for x greater than 0, we conclude that the same must be true of psi x, whose graph is then represented, the value of the maximum at x equals pi over n plus 1/2 is this psi of pi over n plus 1/2 equals 2 times the integral from 0 to pi of sine u over u du plus pi equals 1.18 pi plus pi equals 1.092 pi. So what this 1.8 in is basically the integral from 0 to pi of sine u over u du. Or complementary sine. Sine x over x is complementary sine c. So the integral from u to pi of sine c of u du. Twice that. Where the integral has been obtained from the tables. So it's described that this integral does not have an analytical closed form because it's obtained from the tables. Similar calculation shows that minimum at -2 pi over this quantity 2n plus 1 is approximately equal to negative 0.092 pi. To sum up, the abscisses of the maximum and minimum surfaces of psi approach 0 as n goes to infinity, and at the same time, the slope of the origin increases indefinitely. This allows Snx to approach fx, reach x not equals 0. However, for large n, we see that the amount of the overswing is always near 9% of the total jump at the discontinuity, and the value is independent of n. This is the Gibbs phenomenon for f. Of course, the presence of the phenomenon in a single example or in a collection of examples does not imply its existence in the general case, but in 1906, Machine Boucher of Harvard University, who was not familiar with the work of either Wilbraham or Gibbs, showed that the partial sum of the Fourier series of an arbitrary function always has its overswing of about 9%, meaning jump Dawson's continuity. It is then an intrinsic defect of the convergence of Fourier series. It's a larger bound on the error term for the approximation of the Fourier series. So, I mean, the error term isn't necessarily good or bad. It's just what it is. It's just a value left over. Of course, when you're trying to compute a number and you're supposed to get the right number, it's different from the correct value. But so it's called the error term of the approximation. And as Enrique Gonzalez Velasco says, or the author, it's a particularly associated with the Fourier derivation at these discontinuities about when it when it jumps from the point to over a discontinuity, and then all the way to that is symmetric about when this function is symmetric where it goes to. So it wasn't really put up that in the development of showing what the value was, it wasn't really put up that it was so for just arbitrarily large or small jumps. It was shown that it was so for this kind of even function and given a derivation and provided a value and then pointed to a symbolic calculation of the value and so given. Then that for these other ideas of these other functions that in a Fourier analysis is, but it's what's sort of a family of orthogonal functions transform analysis, but here we're calling it Fourier analysis in the n-gonometric or what. It would have a different derivation because it would have to make use of whatever identities and stuff that could be figured out that make it so that for things that are well known and have very well explored identities and these kinds of things, because they're particularly central and tractable, by their very nature, sine and cosine, for these other any of these other ideas of these other orthogonal functions, like this semicircle wave, or the squares roll wave, and this kind of thing, that it would have a different derivation and may have different values, but it would still be kind of the same effect, overshoot and ringing, da da da. All right, and then the next section is Fejer sums, Fejar, Fejer, but we'll pick that up some other time. Hey, have a great day.